History.
This is going to be parts B1 and B2 of the 2016 Regents exam. I find the B sections to be kind of tricky, probably the trickiest sections of the exam. C is not so bad as long as you are good at writing things down and stuff like that. So, all right, let's get to it. 36. Hopefully you've done the exam already and checked your answers. I will be going into things other than just the question as I see fit. 36. Which measurement is closest to 1 times 10 to the minus 2 meters? All right, so what is 1 times 10 to the minus 2 meters? What is that? Well, there's a word for that, and the word is centa. That's centa. That's 1 centimeter. All right. Well, so we're looking for a centimeter. So we got diameter of an atom. I don't know how big an atom is. I know it's really small. It's not a centimeter, because a centimeter is about that big. All right, here's a ruler. And a centimeter, of course, it's the, a lot of times when it says mm on here, millimeters, but the tick marks are actually centimeters, 1, 2, 3, 4. So centimeters, about this wide. So you'll have a ruler on the exam, so there's no reason for you not to know how big a centimeter is. You need to be able to recognize that that's centa. So this is 1 centimeter. All right, which is closest to a centimeter? Diameter of an atom. Well, no. An atom's much larger than that. Width of a student's figure. Well, I would say it's probably going to be a couple centimeters anyways, but it's kind of close to a centimeter. Length of a football field. I know what you're thinking. Well, I've never played football. The football field's a big thing, and if you're not familiar with the football field, like a soccer field or a baseball field, it's enormous, right? Not a centimeter. And height of a school teacher, right? Well, no, a centimeter. I'm a school teacher, and no, it is the width of a student's figure. All right, so a lot of this is just being able to interpret this number, making number sense of this. That's centa. Let's review. Multiplying by ones. Let's say I had 36.9 times 10 to the minus 9 meters. Oh, let's make that 10 to the minus 7. How many nanometers is that? All right. So if they ask that, I need to look up in my Regents reference table what nano means. And I think nano, which is lowercase n, which is 10 to the minus 9, I believe. Yes, 10 to the minus 9, and 10 to the minus 12 would be pico. All right, so there we go. Nano is that. So we're going to multiply by ones. We want to get this. How many nanometers is that? All right, so what I'm going to do is, I got it in meters. I want to put nano in here and see what happens to my number. So what I'm going to do is multiply by ones, because when I multiply by 1, I don't really change anything. I just change how it looks, right? So here we go. Nano. I want nano, so I'm going to put n in there. I want nanometers. So I'm going to put n, and n equals 10 to the minus 9, so I'm going to put that there. All right. So then I just kind of work my numbers out. Let's see. So I ended up with 36.9 times 10 to the minus 7 nanometers divided by 10 to the minus 9. All right. Well, what is 10 to the minus 7 divided by 10 to the minus 9? I believe that is 10 to the 2, right? 36.9 times 10 to the 2 nanometers. 10 to the 2, right? I think so. I don't have my calculator here, but I think I could do that in my head, right? So if I wanted that in proper scientific notation, that's a perfectly valid number, by the way. It's just not proper scientific notation. Let's move this here, 3.69. I made this number smaller, 36.9. I made it 3.69. So I made it smaller by a factor of 10. So let's make this bigger nanometers. 3.69 times 10 to the 3 nanometers, right? Also, this could be 3690 nanometers, right? So this is probably be more, or 3.69 picometers, actually. But anyways, there we go. Multiplying by ones. It's a wonderful thing. Very simple thing to do. Hopefully you understand how to do that now. 37, our first graphing question. And now students find graphing difficult. Many find graphing difficult. And this is a tricky problem, especially for my students, because I didn't have us graph speed much. I didn't have us graph scalars very often because it gets confusing. So let's actually graph velocity versus time and see how that relates to speed versus time. So here's a velocity versus time axis. We're going to take our object. It didn't say it starts from rest, but let's say we were dropping a ball. It starts from rest, and it's going to drop to the ground. So the ground is going to be here. There's our ball. We're going to drop it. I have myself a coordinate system. This is time t0, and this will be time 1. This is where it's going fast. Right before it hits the ground. Right before it. You know, that's usually where the problem ends. Right before it hits the ground. All bets are off once it hits the ground. And then we got a whole bunch of different physics to deal with usually. So usually when you drop something, you care about when it's a free fall, because the acceleration is going to change rapidly when it hits the ground, and things are going to get complicated. So usually we end a problem right before it hits the ground. In this case, it says, which graph represents the relationship between speed of a freely falling object and the time of the fall near the Earth's surface? Okay, so it can't hit the ground because it's not falling then. So it's got to end before. All right, so there we go. Now, keep in mind, this way's negative, that way's positive, positive, negative, even though we're not doing anything with the x-axis in this case. So let's plot our points. At time t equals 0, this has 0 velocity. We're dropping this thing from rest. Now, it didn't say that in the problem, but that's what we're doing right here. All right, so then at time 1, which is out here, we'll say that's time 1, it's going as fast as it's going to go at v final, right? This is v final. This is v initial here, right at the beginning. V final, let's see, dude. Yeah, that looks pretty good. Now, I have to figure out how to connect the dots. Well, in order to do that, I need to understand the slopes. So let's take a look at the slope. This is velocity. The slope is always delta y over delta x. What is our y? That's v over delta t. What is delta v over delta t? That is acceleration, right? Actually, it's average acceleration, but acceleration. Since it's in free fall, it's going to be a constant acceleration, and we know that acceleration is going to be, in this case, negative g, right? Downward at, or negative 9.81 meters per second squared. All right, so there we go. That's a constant slope, so therefore, it better be a straight line. If it was a curve, is that straight? That's straightish. You're going to want to use a ruler, though. But that's not bad. I'm kind of proud. I pat myself on the back on that one. Yeah, that's pretty straight. Yeah. All right. So, and what is this slope? Slope is negative 9.81 meters per second squared. Notice that's the slope. That's this whole thing. We don't put that on that axis because it has nothing to do with the axis. It has to do with the slope of that line. Negative 9.81 meters per second squared. All right, so that's what it would look like if it was a velocity versus time graph. Now, it's not. It's a speed versus time graph, right? That's what the Regents, they like their speed. So they go speed. So there is no such thing as a negative speed, and that's why you notice they didn't have any sort of negative y-age going. It's all positive, right? Positive people over there at the Board of Regents. Positive group. Not like me, you know. Sometimes I notice the dark things. But anyways, let's get back to positivity. So we got speed. You can't have a negative speed. Speed is a magnitude. There's no such thing as a negative speed. So we still start at 0 speed, and then we end up going faster at the end, like that. Here's our time 1 again. And this is speed final, not velocity final, but speed final. And it is a positive number. And then we go like this, and we go zoink like that. And what is the slope? The slope is 9.81 meters per second. Now in this case, it's not negative. See, this is where it gets confusing. This is why I don't like this. Now it gets confusing. Because technically, the slope of a speed versus time graph really isn't acceleration. I mean, if it's going in a straight line, it's the magnitude of the acceleration. But you have to know it's going in a straight line. If it's not going to, now if it is, it's dropped. If it's dropped, it is going in a straight line. But if it's in circular motion, uniform circular motion, see, this is, anyways. That's why, if you look at this, there's negative stuff, so don't be confused by that. So the answer, I guess, is 4. 4. Speed versus time. Remember, you can't have a negative speed because it's a scalar. So anyway, remember, always do that. Always know what your slope of your graph means. Always plot points, and then from the points, figure out how to connect those. In this case, it had to be a constant slope. And all right, there we go. A hairdryer with a resistance of 9.6 ohms operates at 120 volts for 2.5 minutes. Oh, minutes, that's not a standard unit. The total electrical energy used by the dryer, all right. It looks like we're gonna have to use the Regents reference table. All right, so we have this hairdryer. And it's plugged into the wall. So we got some sort of voltage source, and it goes into, there's my hairdryer, right there. We're gonna represent it as a resistor. It's a hairdryer though, and it's plugged into the wall, right? Well, why don't we go like this? Because walls are usually, so we plug it into the wall, 120 volts. Did they give us the voltage? Yeah, they did. And hey, wall voltage is 120. V equals 120 volts. So we're supplying 120 joules per coulomb to this hairdryer, even though it doesn't look like a hairdryer. Here, I'll make it look more like a hairdryer. It's a blow dryer. There we go. Oh, man, I don't know what. Anyways, there's my hairdryer. Shoots hot air right there. I know what you're thinking. That's not hot air. All right. Hot air. There we go. 120 volts. What else do they tell us? The resistance of the hairdryer is 9.6 ohms. And it's going to operate for 2.5 minutes. All right, we're going to have to do a unit conversion. Let's do that right away, I think, because we're going to need to know the electrical energy, E. Now, we don't use E here. Usually we use W because for electricity, E is reserved for electric field, right? So we use W, work, which is generic representation of energy. What is the energy this thing uses? All right, well, first thing I need to do is I need to get this in standard units. So my answer's in standard units because, their answer's in joules. All right, so I'm gonna multiply by ones. What's my relationship gonna be? Well, what do I know about minutes? I want to go minutes a second. I know that 60 seconds equals 1 minute. All right, so that's what I'm going to do. I want minutes to go away, so I got 1 minute. I'm going to put that right here. And 60 seconds, I'm going to put right there. All right, minutes go away. I know what you're thinking. That's a min, and that's a minute. How do they cancel? Well, think about it. You'll figure it out. So there we go. What's 2.5 times 60? That's 120 plus 30. Is that 150? 150? All right, so let's look at our Regents reference table. Work or energy is, let's see, V. We have V, R, and T. V squared over R times T is energy. 120 volts squared divided by 9.6 ohms. Don't forget to square that. 150 seconds. All right, I got 2.25 times 10 to the 5th joules. Is that an answer? That looks like it's 4. 4. All right, they had two significant figures because, yeah, they should have been. Because that was 2 and that was 2. And, all right. A box weighing, this is number 39, a box weighing 46 Newton rests on an inclined plane that makes an angle of 25 degrees to the horizontal. What is the magnitude of the component of the box weight perpendicular to the incline? All right, the dreaded inclined plane problem. Let's take a look. Not so bad once you get the hang of it, but you know, it's all about getting the hang of it. So we got ourselves an inclined plane. You're always going to draw what's going on. Here's my box. What is it that's on there? A box, hey, and I drew a box. Nice. I'm psychic. All right, I got to circle the object of interest. That way I understand the contact forces. The only thing in contact with the box is the inclined plane. And what angle is this? That's 25 degrees. 25 degrees. All right. Now, all right, so I'm going to draw my coordinate system. And what I'm going to do is tilt my axis, because anytime there's an acceleration, we want to make sure it's along one axis. So that's what we're going to do. If this thing's going to accelerate, it's going to accelerate down the ramp. So I'm going to make that my x-axis, and I'm going to make the y-axis like that. Make sure they're perpendicular to each other. You know, it's not unusual for me to see people do things like that. No. These have to be at right angles. Don't do that. Makes me sad. Cry myself to sleep at night. All right, here we go. I'm going to use a particle model. I'm going to simulate the box as a particle. And let's see, what are the contact forces? Well, is this frictionless? We don't know. We don't know much about this. So I don't know if there's friction. If there is friction, and this is a simple problem, hopefully, for the Regents. Let's say it's actually sliding down the ramp. If we're sliding down the ramp, then friction would be this way. All right. I don't know if there is friction. I don't think it's going to come into play in this problem. So we have friction. If it's sliding down, friction opposes that. We also have a normal force. Normal, of course, means perpendicular. So F sub n, that's the ramp pushing up like that. And those are all our contact forces, right? That's the only thing in contact. So now I'm going to draw force at a distance, which is a force of gravity, which is always straight down towards the center of the Earth. F sub g. All right. Now, of course, what we're going to do is, when in all these problems, we need to identify where's that 25 degrees. Where is that? Well, this is the angle right here. It's always with the y-axis here. 25 degrees right there. I like to do a thought experiment where I imagine if I collapse this down to 0 and that goes to 0, which angle would go to 0 here? And you would see that as this collapses, this is the angle that would go to 0 as that went to 0. Well, that has a couple of components. We want to make our lives easier mathematically, so we say this is the force of gravity that is down the ramp or in the x direction, and this is the force of gravity in the y direction. Those are our vector components. What is the magnitude of the component of the box's weight perpendicular to the inclined plane? All right, so here's the weight and the component. Now, that's why we didn't need this. We didn't even really need that. But the one perpendicular to the inclined plane would be FGY. And what is FGY? Well, that is going to be the total weight times the trig function that involves this side of the triangle and the hypotenuse, because this is the hypotenuse. All right, well, that's the angle. This is the opposite side. This is the adjacent side. And the trig function that involves hypotenuse and adjacent, of course, is cosine. FG cosine of 25 degrees. And let's see. What did they say FG was? 46 newtons. 46 newtons is the weight times the cosine of 25 degrees. 41.7 newtons. 41.7 newtons is the answer. All right, to two significant figures, that would be 42 newtons. And that was the answer, which is choice 3. Choice 3. All right, I had a comment on one of my other videos recently where a student asked, isn't this component always cosine? Because they looked at something, I think, I don't know why, but on your Regents reference table, they have some garbagey relationship, like they say AX equals A. I think they're looking at something like this, where they're saying, all right, there's A, and this is AX, and that's AY, and that's our angle theta. So they're saying that AX is always A cosine of theta, and AY equals A sine of theta. I think that's in your reference table. That's a terrible thing that the Board of Regents does. They're terrible people.
Shame.
Maybe I shouldn't say that.
Shame.
Maybe I shouldn't attack the state because I don't know, they could take away my license or something. But anyways, I'm sure they're not really terrible people. But why did they do this? Because this isn't always true. It's not even true here. It's not true. Ignore this. Don't use the reference table for trig. No, don't do that. That's a terrible thing. The first thing you do when you get your reference table is cross that out. Rip it out and eat it. You might want to bring some ketchup or pepper or something like that to the exam because eating plain paper isn't that tasty. So bring some spices so you can rip that out and eat it. No, don't eat it. It's probably toxic. Don't eat it. I'm only kidding. I'm a kidder. That's what I do. Which graph represents the motion of an object with a positive velocity and a negative acceleration? All right, here we go. So what do we got here? We got, notice we only have positive things here. So we have a position versus time graph. All right, and we're only positive on this. Let's talk the x. So we got something moving here, and I don't know. Let's make it a cart, and it's on the x-axis, and we're starting at different positions. Some we're starting at 0, and anyways, all right. There's position versus time graph. Well, that way's positive, and that way's negative. That's our standard. What are we looking for? Positive velocity, and negative acceleration. If it has positive velocity, it must be headed in the positive direction. Is 1. So they're starting like here, right there. And then they're ending up some place here later. All right, it goes like this, like that. Now, what is this slope? Slope equals delta x over delta t, which is velocity. That is a positive velocity, and it is a constant velocity. So a equals 0, because the a acceleration is delta v over delta t. But that's constant. So I don't think that's a negative acceleration. I think that's a 0 acceleration. All right. So I'm not liking 1. Let's take a look at 2. This is looking more acceleration-y. 2. All right. So this thing's starting here and there. Okay, I buy that. And it goes 0, 1. 0, 1. It is, the slope is always positive. Yep, it's always tilted that way. And it is changing. It is changing, so it is accelerating. Now is that this thing is actually, what's this thing doing? It's starting off at a high velocity and going, so it's slowing down. It's going this way, and it's slowing down. That is a negative acceleration. A negative acceleration is that way, so we want it accelerating this way. So it needs to be traveling this way. It needs to have a velocity this way, but it needs to be slowing down, right? Because we need an acceleration vector in the opposite direction. We need an acceleration vector that's negative, right? Negative doesn't mean slowing down necessarily. Negative means it's in the negative direction. So there's a positive velocity and a negative acceleration. It's slowing down. So here we go. This thing is slowing down. It's starting with high velocity, and so I'm liking 2. Let's take a look at 3. That's a 0 acceleration. And it's a negative velocity. It's a negative slope, so that's a negative velocity. So this is negative velocity, and a equals 0. So that's no good. 3 is no good. Right, let's get rid of that. Let's get rid of that. I'm liking 2, though. Let's take a look at 4. 4. Oh, look at that. All right, so this thing starts off 0 velocity, and it's going fast at the end. But the slope is always negative, so this is a negative velocity. This is negative velocity. This isn't going that way. It's going that way. Because it's starting out with a positive value and then going to 0. It's going that way. This is a negative velocity. That's a negative velocity, so it's going this way, and it's going this way, and it is speeding up in the direction of its velocity, so it is also a negative acceleration. But that's no good because of the negative velocity. So it looks like 2, I'm thinking. I'm thinking 2. I'll hear about it on YouTube if it's not. Man, it wasn't 2. So check that out. Car A is moving in a straight line at constant speed. All right, so constant velocity also. All right. I think I'll have A go in the positive direction. VA, I'll call that. What is VA? It's Veterans Administration. 20 meters per second. All right. Is initially 200 meters behind car B. All right. Car B. I hope car B is going at constant velocity too. In the same straight line, oh, beauty. At a constant oh man, they're going to crash. All right, so it's going a little slower. VB. VB equals 15 meters per second. All right. And the distance between them is 200 meters. It's a distance, right? 200 meters. How far must A travel? Distance of A. For smash. They're smashing the cars. They are what, man? Remember when I said the Regents people were positive people? This seems kind of dark. They're like, okay, he's got a long time. He's going to smash into this car. All right. Well, anyway. What is that? This is really the easiest way to solve this. This is a relative velocity problem, which the Regents doesn't get into very often. So many of you are probably confused because you haven't seen questions like this. What I would do in a problem like this, I would say, how fast are they moving relative to each other? So if I just look at this and say, okay, well, VREL is 5 meters per second, right? This has a velocity of 5 meters per second relative to B. You know, it's going a little faster. If they're going the same speed, then they would have a relative velocity of 0, right? But they actually have a relative velocity of 5 meters per second. So this is, as far as this is concerned, if it's just looking, if he didn't see the rest of the universe and he just saw that car, he would just think, well, I guess I'm moving at 5 meters per second. So I'm going to do this in 2 parts. Number 1, I'm going to figure out, I think, how long does it take for these things to smash into each other? So I'm gonna solve for time. So I know that their relative velocity is 15 meters per second, and I'm going to use this relationship from your reference table. Average velocity equals distance over time. Luckily, we're all going at constant velocities. So So time to crash. I'm going to calculate how long is it going to take to crash this thing. All right, so time to crash is the distance that they need to cover to crash, which is 200 meters, right? In its world, the A just sees, oh, I'm 200 meters away from this car, and that's how far it's going to have to travel. 200 meters divided by 5 meters per second, right? That's how fast it's going relative to that car. And it's got to make up that 200 meters. All right, so what's 200 divided by 5? 40? Is that right? 40 seconds? Now, the question, though, was how far does A travel? Right? How far must A travel for this initial position, from this initial position before the crash? Well, it's going to take 40 seconds to make up this 200 meters. So we're going to go, all right, let's see. How far does this thing go? So distance A travels is the average velocity of A times the time it's going to take for the crash. And how fast is VA going? 20 meters per second times 40 seconds is 800 meters. It's going to take 800 meters. Let's see. That's choice 3. Choice 3. Well, if you didn't know how to do this, you could have guessed, sort of. You know it's going to take more than 200 meters because once it gets to 200 meters, that B's not there anymore and it's moved a bit. So you could eliminate 200 meters. 400 doesn't sound right either. If I was guessing, I would have guessed either 3 or 4. Choice 3 or 4. Turns out it's choice 3. But because I don't guess. Don't guess unless you have to. That was an unusual problem. They don't usually have those relative velocity problems on the exam. I bet a lot of people didn't get that one right. A 2,700 ohm resistor, 2.7 kilo ohm resistor in an electrical circuit draws a current of 24 milliamps. The total charge that passes the resistor in 15 seconds is... All right, let's get out the Regents reference table.
Regents reference table.
All right, so we have a resistor in a circuit. Oh, well, they didn't give us much information. Here's our resistor. I would imagine there's some sort of source of potential difference. Maybe a battery. Probably not. I'll put a battery in there. There we go. Resistance is 2.7 kilo ohms. I'll write it out how they did it. 27 ohms. There's a current traveling through here. I is a 2.4 milliamps. Okay. What is milli? Milli is 10 to the minus 3. Look that up in your reference table.
Reference table.
Milli. You got to get that into you need because your calculator doesn't understand milli. It doesn't understand milli like I understand milli. And it 15 seconds. All right. It's a standard unit. I'm glad. What's the question? What's the total charge that passes by? They use a delta in there for passing by. Delta Q. So we need to know Q is our charge. Keep in mind on your reference table, your Regents reference table, they have like this. They have all the symbols there. If you forget what charge is, look it up. You have 3 hours. You know, so you might as well use the time. You spend all this time this year. You might as well use it well in class and during the test. Do as well as you can. All right. How much charge is passing? Well, I know that current is defined as the amount of charge that passes in a certain amount of time. And so I want to know how much charge passes. Delta Q equals I delta T. Well, guess we don't need that. All we need to know is charge passing by just the current, really. So we got 2.4 times 10 to the minus 3 amps times 15 seconds. Yeah, right, whatever that is. All right, didn't need that. That was a distractor, as they say. I don't know why they call it that. You know? That's not really a distractor. A distractor is when someone goes, you can't, I'm not touching you. That's a distractor. That didn't distract me at all. But if someone's going like that, that's a problem. I would be distracted by that. 3.6 times 10 to the minus 2 coulombs. Get off my futon. Doolom. All right, I guess that's choice 2. These problems, one place you have to look at is make sure we're in the right units whenever we have charge. We have 2 types of units. We have elementary charges and we have coulombs. Whenever you're using these in these equations, if you're going to come up with an answer in standard units, make sure that's always going to be in coulombs, not elementary charges. A 1,000 kilogram car traveling 20 meters per second east experiences an impulse of 2,000 newton seconds west. What is the final velocity of the car after the... All right, so we got vectors here. We better pay attention to direction. We better draw a picture too. 1,000, okay, so it's going east. All right, standard. East is that way. West is that way. That way's positive, that way's negative. All right, here we go. We got a car. 1,000 kilograms. The mass of the car is 1,000 kilograms. It is 1,000 kilograms of stuff. If I took that to Jupiter, it would still have 1,000 kilograms of stuff. Its weight would be different. It'd be really hard to, very cumbersome on Jupiter, but it still would have the same mass. It would still be just as hard to wiggle it back and forth. Exactly the same difficulty to wiggle it back and forth. Although lifting it would be brutal. But you'd have other problems, actually, if you're on Jupiter. We won't go into that right now. It's traveling 20 meters per second east. So velocity initial, that's initial, is 20 meters per second. And that's positive. East is positive. Whenever you got these impulse things, you better take into account direction. So I'm going to make sure that I'm thinking positive, negative. All right. It experiences an impulse. Impulse is also a vector. 2,000 Newton seconds west. Negative, right? I'm using negative as a proxy for west because my calculator doesn't understand west. It's not like Siri. West! Nothing, right? So it doesn't understand west. It does understand negative, right? Negative.
Thank you very much. I fully understand that.
See? What is the final velocity of this cart? All right. So we're going to need direction. All right, so this thing's driving like that, and it's got a velocity, and there's an impulse. What is impulse? Impulse is, not using calculus is difficult here. So impulse is average force times time, right? I don't know that they actually put, and it's net force, Ben. On your Regents reference table, I don't remember if they put the average. But that is average. Otherwise, you have to use an integral. But we're not going to do that here. We're going to use the impulse change in momentum theorem. This is derived from Newton's second law. It's just a reworking of Newton's second law. Impulse causes a change in momentum, right? There you go. The long lost theorem that students often forget about. So they gave us the impulse. And we're going to use scalar operations. Now this is vector, but we're going to use the negative as a proxy for the vector, and we're actually going to use a scalar operation. We're going to use plus and minus to take into account the vectorness of things. All right, so this is P final minus P initial is delta P. But what is P? P is MV final minus MV initial. We can factor out the M's. The M doesn't change, so I can rewrite this. And this is typically the more useful form of the impulse change in momentum theorem, because the momentum in these problems, or the mass doesn't change. This isn't rocket science after all, where the mass actually changes. So you got something like that. This is going to be the useful form. You want to be able to do that real quickly to go from here to here, because it's going to be a more useful form. I'm going to solve for V final. So I end up with impulse, divide by mass, V final minus V initial. And then let's go one more time. Let's get that V initial on the other side. And there's our relationship. And we're going to be golden as long as we take into account our positives and negatives. We had minus 2,000 Newton seconds divided by the mass, 1,000 kilograms. Oh, I hate it when I'm so low. V initial is positive 20 meters per second with V final. All right, so 2,000 divided by 1,000, that's 2. So this is looking like this is going to be 20 minus 2, which I believe is 18 meters per second. And it is indeed positive, so the answer is 18 meters per second east is the answer. That's what you do if that was a long answer problem. So I guess it's 1. So if you didn't take into account the opposite direction, you would have ended up with 22, but it would have been positive. So you should have said, oh, 22. See, they were nice here. She got that 22 there, but it says west. And since you didn't get a negative value, you should have said, well, there's a problem there. But I know many of you would have just said, well, I'll ignore that problem and just circle that because my calculator says 22, and there's 22 right there. And that would be bad. They actually would help you out by just saying, hey, why is that west? Which graph represents the relationship between the potential difference applied to a copper wire and the resulting current in the wire at constant temperature? This is Ohm's law. Ohm's law says that the resistance of an ohmic device, as long as you keep the constant temperature, the resistance will remain constant. And we have this relationship where we have, I think in your reference table it says this. I don't know. R equals V over I. So let's get this in graphing terms. Let's use extreme physics, right? We got to get this in regular graphing term, and where the voltage is our Y, so we got to isolate that on its own. So I'm going to rewrite this as V equals IR, right? So that is the a proper way for extreme physics, right? So we got V and I. All right. So if something obeys Ohm's law, the resistance is going to remain constant. So let's practice our extreme physics. All right, so we have I and we have V. All right, let's put in a extremely small number for I. 0 if possible. Can I put 0 in? Yes. If I put in 0 for I, 0 times whatever R is gives me a 0 voltage. All right. Now let's put in extremely large. So I'm going to put in a large number, large, for this. So if I put in a large number for I times whatever R is, I'm going to get a large number for V. So let's plot those. 0, 0 is right there. And large, large, I is large, V is large. That's right up there. Now, since it's ohmic, let's rewrite this. V equals Ri. That way we can see this is like Y equals mx, right? Where this is our slope, and because it obeys Ohm's law, it is constant. So this is going to look like that, where the slope equals R. R. Pirate Day here at the Regents exam. R. I guess 1. Choice 1, it looks like. Often people say this is Ohm's law. Technically, it's not. This is a relationship between voltage, current, and resistance. Ohm's law says that if a device is ohmic, as long as we don't mess with the temperature too much, this R is going to remain constant. So if we bump up the potential difference, we will proportionally bump up the current, right? And the constant of proportionality will be R. A tungsten wire has a resistance R at 200 degrees C. A second tungsten wire, twice the length and half the cross-section area. All right. This is proportional thinking if there ever was a question. I love proportional thinking. That's the beauty of physics. A tungsten wire has a resistance R. All right. So in the first case, we got this wire. And here it is. There it is. It's made out of tungsten. R1. It has a resistance. We can figure out the resistance of something by hooking it up to a battery, right? And we can find the resistance by using this relationship, V equals IR, or actually R equals V over I. And all we have to do is apply a potential difference here. Let's measure that. Measure the potential difference. Measure the current through that. And experimentally, we can find the resistance. Beauty! That's fantastic. But we can also figure out the resistance if we know the physical characteristics, and that is if we know the resistivity of the material. And there's a table of resistivities on your Regents reference table.
Regents reference table.
And we know the length, and we know the cross-sectional area. All right, so in this case, we have a hunk of tungsten wire at 20 degrees C. Beauty, that's the temperature in our reference table.
Regents reference table.
Is R. All right, it has resistance R. A second wire, what is it? Oh, it's smaller in cross-section. Well, that's kind of hard because I already drew this one small. But here we go. But it's twice as long. So there's our second wire. So R2 is the same material. It's tungsten. So that's resistivity. That's the material. And what is the length? The length is now 2L. It's twice as long. Half the cross-sectional area. So it's the area divided by 2, right? If that's A, it's cross-sectional area, right? But divided by 2. Now, some of you, I know, are going to struggle with the improper fraction. So what I'm going to do is, to get rid of that, I'm going to multiply both the top and bottom by 2, right? As long as I do the same thing at the top and the bottom, I don't actually change the number because 2 over 2 is 1. We're multiplying by 1s here. All right, well, that makes that go away. And we end up with rho 2L2 divided by A. Well, let's multiply these together and factor those out. So that is 4 rho L over A. But what is rho L over A? Well, that's R. This is 4R. Does that make sense? We made this thing skinnier and we made it longer. We really bumped up the resistance. It's 4 times bigger. So 4R, I guess the resistance to the second wire is 4R, so that is choice 4, I guess. Choice 4. Oh. Could have guessed it that. 4R and 4. Could have saved myself some time. Because the 4s match. I wouldn't advise using that technique. It's a time saver, but it's pretty unreliable. After an incandescent lamp is turned on, the temperature of its filament rapidly increases from room temperature to its operating temperature. As the temperature of the filament increases, what happens to the resistance? All right, so when things get hot, you just need to know, and there's a clue that temperature affects how easy it is to move charge through objects. And if you look in the reference table, it says resistivity of certain materials at 20 degrees C. That implies that it changes with temperature. What you need to understand is, and you just need to know this, that as the temperature goes up, it's harder to move the current through the wires, and the resistivity goes up. All right. So here we go. We have we have some sort of voltage source, and we have an incandescent lamp. There we go. There's our lamp symbol. This is not a voltmeter. That'd be true. This is a source of potential difference, right? Actually, I'll make it as a battery, so that way no one's confused. Is turned on, the temperature of its filament rapidly increases. So it looks like the resistivity is going to be going up, and therefore the resistance is also going to be going up because the resistance equals rho L over A. The length of the filament doesn't change. The cross-sectional area doesn't change, But if the resistivity is going up, the resistance is also going to go up. Resistance, okay. So, and then the current that's going through this circuit, or through the lamp, which is going to go through the whole circuit, equals I equals V over R. All right. So the voltage is going to stay the same, but what's going to happen is the resistance is going to go up. So what's going to happen to the current? The current is going to drop. The current is going to go down. Resistance is going to go up. Current's going to go down. So which one is that? The resistance increases and the current decreases. Yes, choice 1. I always like to check the other ones just to see. The resistance increases and the current increase. No. Well, this one isn't so much fun because it's just mix and match. All right. So the key here is to know as the temperature goes up. Remember I had the screaming electrons? I'm going, la, la, la. You know, I wish I could play Flash. Premiere doesn't allow me to play my Flash animations. It's very sad. Parallel wave fronts are incident on an opening in a barrier. I bet they're going to use diffraction. I bet this is a diffraction question. Which diagram shows the configuration of wave fronts and barrier opening that will result in the greatest diffraction of the waves traveling through the opening? All right, remember what diffraction is? Diffraction is the bending of a wave around barriers, I guess, right? So it's a bending of waves around barriers. The smaller the opening, the more bending you'll get because it sees more barrier. What we're looking for is a small opening. Now, what makes something a small opening? It's relative to the wavelength. You want the opening to be small compared to a wavelength. So it's looking like 1 and 2 look like they have the same size openings, and they're smaller than 3 and 4. So 3 and 4 are out of the question in this case because those are larger openings. So 1 and 2. So which one is a smaller opening compared to a wavelength, right? And it looks like 2 is a smaller. It looks like 2 is actually a little less than a wavelength, and 1 is larger than a wavelength. So the choice is 2. 2. So what we would have here in 2, you have your opening like this. You know, this little section here is going to go through, and we get bending around the edges. But since it's a small opening, the whole thing looks like edges. So you end up with something that kind of goes like this. Kind of like that. The way I didn't do a very good job. These wavelengths should remain constant, but I'm not going to take the time to draw that a little more. Now, if we take a look at the one with the least diffraction, it has a large opening compared to the wavelength. That would be 3. And what would happen on 3 is something like this. That opening looks kind of big compared to wavelength, right? I might be exaggerating here. But this is what happens when the opening's big. So this wave goes through because there's nothing blocking it. And then you can think about this. That wave kind of keeps doing what it's doing, right? But we get curving around the edges. So we would say this is less diffraction. And it goes like that. All right. So anyways, know how to draw your diffraction patterns. There's 4 of them. You have something going through a small opening, large opening. Make sure you can do that. A small barrier and a large barrier. All right. So make sure you can do that. This is a large opening. Let's take a look at the barriers real quickly. A small barrier looks like this. And what's interesting about a small barrier is that the wave passes through unaffected. When the barrier is much smaller than the wavelength, it's really not going to affect the wave at all. That is what a small barrier looks like. See, it's small compared to wavelength. And a large barrier looks like this. You can see wavelength's only that big. So what's going to happen is, so out here, these aren't affected. But what they do is you start getting like that. Kind of like that. Something like that. And if you get far enough away, it's like the barrier wasn't there. But we do get a lot of bending. We do get a shadow here. I probably shouldn't have drawn in. So something like that. Here, maybe I'll pop up a drawing there. Maybe it's there. Maybe it's not. I don't know. A singer demonstrates that she could shatter a crystal glass by singing a note of wavelength 0.320 meters. In air at standard temperature and pressure. Oh, what is the speed of sound at standard temperature and pressure? I think that's 331 meters per second. Oh, it's cold. It's at 0 degrees C. She's singing cold. I hope it doesn't break. Oh, it does break. Maybe she wanted it cold, so it broke easier. What is the natural frequency of the glass? All right. Remember that guy? Remember the guy with the glasses? Dude, he's my favorite guy. Maybe here he is right now. I don't know. I'll see if I can dig up that video. Fantastic guy. I like that guy a lot. All right. Yeah! So we want to know, what's the question? What's the natural frequency? What's the resonant frequency? What's the frequency she had to hit? Because if you ping the wine glass, or whatever, the crystal glass, it will have a natural frequency. And if you sing at that frequency, you will cause it to resonate, and you get constructive interference. You set up these standing waves, and a small amount of energy can actually do a lot of damage. So this is that is the phenomenon of resonance. When you excite something at its natural frequency, and you get a large wave, that's resonance, and that's what's happening here. So the standard relationship, speed equals frequency times wavelength. Yeah, hopefully you're good at that. It's on your reference table. So let's solve for frequency. Frequency equals speed divided by wavelength equals 331 meters per second divided by the wavelength, which is 3.32 meters. All right, so what do we have? We have 1.03 kilohertz, or per second. So that is choice 3, which is, they wrote it like this, 1.03 times 10 to the 3 hertz. If anybody ever asks you if you want a Hertz donut, say no. I learned that from my father. Diagram below represents a standing wave in a string. Keep in mind, with a standing wave, this is never actually happening. The string is never here and here at the same time, right? It's either here, or it's here, or it's in between. So it sets up this envelope of, like this. It turns into a blur. And there's sometimes when it's like that, right? So it's all that. So that's what's happening. Let me redraw it as we normally do. So this thing's shaking about. All right, so now we got these one areas where sometimes we have a large amplitude and sometimes it's 0. But sometimes it's really large. This is called an antinode. Antinode. Right? There's one here and there's one here. Right? This whole area is an antinode. This is not an antinode, and that is not a separate antinode. This whole area is an antinode. This is an antinode. Now we got this area where you never have an amplitude, and these are called nodes. Node. There's 3 of them in this. 3 nodes and 2 antinodes on this particular one. Now, and the reason standing waves occur is because we have 2 waves. We have a wave going this way and a wave going that way, and they are interfering with each other, right? You get a standing wave when you have 2 waves in the same place at the same time, traveling in opposite directions of the same frequency, same wavelength. They're the same waves, only except they're traveling in opposite directions. In this case, it's occurring because there's a reflection between them. What is the maximum constructive interference occurs at, here we have constructive interference, here we have constructive. Here we have destructive interference, and same thing there. So at our antinodes, which are, maximum constructive interference occurs at B and D at the antinodes. Maximum destructive interference occurs at A, C, and E, and those are nodes. Remember, there is no amplitude on a node. No amplitude on a node. No amplitude. The amount of amplitude at a node is none. All right, so what's the answer? I guess it's 3. Know your standing waves. Which circuit diagram represents a voltmeter connected correctly to measure potential difference across R1? All right. Now, remember, our electrical devices have to be designed in such a way that they don't affect the thing they're measuring. You don't want your measuring device to affect the thing you're measuring. So a voltmeter, here's my voltmeter. And if we want to measure something, like if we had a resistor like that, we would connect it kind of like that, and we would measure the potential difference between here and here, right? With a voltmeter, and since we don't want it to affect the circuit, the current's going around like this. We want all the current to continue to go through here. We don't want any current to go in here. So this is R equals infinity in an ideal circuit or an ideal voltmeter. Now, if we wanted to measure the current through, we actually have to put an ammeter. We actually have to open up the circuit, and an ammeter has to be in series like that. We don't want the current to change from the point at which before we had the circuit. So our resistance is 0 in an ideal circuit, all right? So there we go. That's how we connect an ammeter. We connect an ammeter in series with the thing we're interested in, and a voltmeter in parallel. And the resistance of a voltmeter is infinity, and the resistance of an ammeter is 0, an ideal one. In reality, it's just very large and very small. So let's take a look at number 1. I don't know, I see a problem. I just put an infinitely large resistor in series, and no current's going to flow in the circuit. So I've just changed the circuit. So no, that's not going to happen. And actually what this would end up doing is no current would, this would actually just measure the battery voltage. So that's no good. 1's no good. 2, let's see, what would happen if I put a voltmeter here? Would that affect the circuit? No, not really. I put an infinite resistance from here to here. That's okay. But what does this measure? This is actually just measuring the potential difference across the battery and also the potential drop across R1 and R2. So that's not what we want. 3, and we put our voltmeter there. That's not going to change anything because it's infinite resistance. That's not going to affect the circuit. Beauty. Will it measure the potential difference across R2? Yeah, it will. It will measure the potential difference across R2. It's connected across R2. It's also connected across R1. And also connected across a battery. So in this case, it's going to read the battery voltage, which is the R1 voltage, which is the R2 voltage. All right? And so look, that looks good. Let's take a look at 4. And then we put a voltmeter here. Oh, we just put an infinite resistance here. We've just changed the circuit. That's a bad thing. Because now we've blocked any current traveling through here because that has infinite resistance. And what are we actually measuring here? Here we would just be measuring the battery voltage. So 3, as represented in the diagram below, constant 15 Newton force is applied to a 2.5 kilogram box, accelerating the blocks to the right, blah, blah, blah. Calculate the magnitude of the net force acting on the block. What's the magnitude of the frictional force? We're going to need to draw a free body diagram, of course. We're going to apply Newton's second law. Calculate the net force acting on the block. In your reference table, it looks like this. Of course, in our class, I didn't do it this way. We tended to go, sum of the forces equal mass times acceleration. Doesn't matter either way. This is the net force the vector sum of all the forces, technically like that. But anyways, so we want to know the net force. F net equals mass times acceleration. What's the mass? 2.5 kilograms times the acceleration. 2 meters per second squared. That's positive. So this looks like it's 5 newtons. F net looks like it's 5 newtons. All right. Object's mass times acceleration is the net force. Determine the frictional force. All right. Well, let's circle the object of interest. And let's draw a free body diagram. Go like that. Got our y-axis and our x-axis. We have 15 newtons applied, right? So I circle the object of interest. I see there's some sort of applied force here. I don't know what it is. And then we also have the surface. The surface is applying a force upward. Call that the normal force. And friction is opposing the motion. That's the opposite. That is, and it has to be less. It has to be less than that because we have a net force that way because it's accelerating. I know because we're accelerating. And then, of course, we also have the weight. Fg. Determine the magnitude of the force of friction. All right, we want to know what that is. All right, so I'm going to use this relationship. Sum of the forces equal mass times acceleration. Well, what is the vector sum of the forces? Well, we have a positive 15 newtons. 15 newtons minus whatever the force of friction is equals mass. Make sure you're doing all this good stuff. On this long answer, write down the equation, whatever it is. Substitution with the units. Answers with the units. All right. Actually, heck with that. I'm not going to do that. Why'd I do that? Let me do this again. So we had 15 newtons minus the force of friction equals mass times acceleration. So the force of friction, therefore, is 15 newtons minus ma, just solving the algebra there. I brought the force of friction over here, brought that over to the other side, equals 15 newtons minus 2.5 kilograms times 2 meters per second squared. Looks like 10 newton. Force of friction is 10 newtons that way. All right, they gave us a lot of superfluous angles. We always measure angles relative to the normal. Some of you, for some reason, that's difficult. We only care about this angle and that angle. 41 degrees. We measure relative to the normal. Only. All right. So there we go. We got going like this. It's looking like it's speeding up because it's bending away from the normal. So light travels slower in the mineral than it does in the water. Calculate the absolute index of refraction of the mineral. All right. Well, first thing you want to think of with index of refraction is C over V. But in this case, we can't use that because we don't have any speeds or anything like. We don't know the speed. So, all right. So we can't use that. So I think we're going to use Snell's law. That says N1 sine of theta 1 equals N2 sine of theta 2. Make your life easier. Why don't we call this 1 and 2? Why don't we label as 1 and 2? So here we go. And we can look up the index of refraction of water.
Regents reference data.
H2O. I believe that's 1.33. I hope it is, because I'm not going to look it up. So we want to know what is N1. N1 equals N2 sine of theta 2 divided by sine of theta 1. N2 is 1.33 times the sine of 41 degrees divided by sine of 27 degrees. 1.92 is the index of refraction, and it should be higher than water because I can see that it is speeding up when it goes into the water. So 1.92 is the index of refraction of the mineral. All right, now we have to be careful. Some things we have to be careful about here. Even if you know what you're doing, sloppiness is going to cause you to lose points. Step 1, write down the equation. Fully write it out. Step 2, substitution with units. A degree is a unit. If you don't have degrees, you will lose a point. Don't lose those silly points. And then answer with units. In this case, index of refraction is the ratio of two speeds, so it has no units. All right. There we go. Oh, the other key is this had to be that our favorite color of yellow, 5.09 times 10 to the 14 hertz. That had to be the, so that we could use our table and use that value for index of refraction for water, because the index of refraction changes with color, with frequency. A ball rolled twice across a level laboratory bench and rolls off and strikes the floor. In each trial, the time it takes for the ball to travel from the edge of the table is accurately measured. All right, so it's going to go, so we got a velocity like that, got a velocity here, and then it is going to, you need to be able to draw the trajectory of an object in projectile motion. So it goes something like that. It's parabolic. The key idea here is that the fact that it's going this way does not affect how long it takes to get to the ground or the rate of the fall. This thing is going to take as long to get to the ground as a ball that I just dropped that wasn't moving at all. What happens in this direction doesn't affect what happens in that direction. So in this direction, we have constant velocity in the horizontal because there are no unbalanced forces. And in the y direction, we have constant acceleration because there is the unbalanced force of gravity. It's in free fall. In trial A, the ball is traveling 2.5 meters per second. So VA equals 2.5 meters per second. The ball strikes the floor at 0.39 seconds. All right, so the time for A to get to the ground from here to here is 0.391 seconds. Calculate the height of the table. So with projectile motion problems, you know how I always had set up the T-chart. We don't need the X, but why don't we do it anyways? Good practice. X and Y, right? So this is a Y problem. We know that it's going to take delta T is 0.391 seconds. V initial, or V0, is 0. Right? It has no initial y velocity. This VA is 2.5 meters per second. That's in the x direction. We also know the acceleration is negative 9.81 meters per second squared. It's in free fall. Calculate the height of the table. What is delta y here? Right? So we got a delta y. What is that? Also d. Those of you not used to me, you can just call that d. What's the distance it fell? That's the distance it fell. So I think we're going to use El Grande. I think this is a job for El Grande. D equals VIT plus 1/2 AT squared. All right, that's El Grande, the big one. All right, so that's 0 because V initial 0. So the height is going to be 1/2 AT squared, 1/2 times negative 9.81 meters per second squared times 0.391 seconds squared. Don't forget that square. A lot of people are forgetting that square. It drops. I got a negative value because it went down. This is actually displacement. Does that make sense? 0.3, so 0.7 meters, about that high. Let's try 1 that. Okay. I'd buy that that's 0.4 seconds. That seems reasonable. There's the height of the table. In B, it's traveling at 5 meters per second. Ooh, twice as fast when it reaches the other table. Compare the time it took for the ball to reach in trial B, the time it took in A. B's going twice as fast. So it's going to land farther out, but The fact that it's going this way has no effect on the downward motion. Compare the time it took. TA equals TB. They are the same. Equals 0.391 seconds. So the time for ball A equals the time for ball B to fall. That's a key idea for projectile motion, that what happens horizontally doesn't affect what happens vertically, right? As long as you aren't launching at an angle. If you launch at an angle, then all bets are off because you're given an initial vertical velocity, which might be different in the two trials. But in this case, it was both of them started with 0 initial velocity in the y direction. A toy plane flies clockwise at constant speed in that circle. Calculate the speed. All right. So I'm not going to get too fancy with my plane because I'm in a hurry. All right. So our velocities are like that. Velocity is constantly changing, but the speed is constant, right? Velocity is changing because the direction is always changing. Calculate the speed. Toy airplane radius is 8 meters, and the acceleration of the plane is 25 meters per second squared. If you look on your reference table, they have something that looks like this. That is, they call that centripetal acceleration. I hate the term personally. I prefer radial, but since this thing's going like this and it's constantly changing its velocity, it is accelerating. And the acceleration vector is towards the center. So is the net force vector. Of course, the net force and the acceleration always have to be in the same direction because acceleration is caused by a net force. So, in something in uniform circular motion, you can look it up in your reference table. This is the magnitude of the acceleration. Calculate the speed of the aircraft. Okay, so what is the speed? Right? What is the speed of the aircraft? So v squared equals AR, or v equals the square root of AR. They call that centripetal acceleration, but it's just the acceleration. Centripetal just means towards the center. And in something in uniform circular motion is accelerating towards the center. 30 meters per second is the speed of the aircraft. State the direction of the velocity at the instant the acceleration is southward. So acceleration here is, and then they gave us, they got this right here, right? They got east, west, north, and south. All right, so here the acceleration is westward. Here the acceleration is northward. Here the acceleration is east. And here the acceleration is south. What do they want? Southward. So it's right up there. So the direction of velocity velocity here is east. V is east when the acceleration is south. Graph represents the speed of a marble rolling down a straight incline as a function of time. Which quantity is represented by the slope of the graph? Oh, this is difficult. It's kind of acceleration if it was velocity. I don't know why they gave us speed, but anyways, I know it's in a straight line, but I guess the magnitude of the acceleration. I hate that they do speed like that. Let's assume it's velocity. Man, I not a big fan. Not a big fan. So we have something like that. And what is the slope? The slope, if it was velocity, is delta V over delta T, which is acceleration. Change in speed divided by time isn't acceleration, technically. But anyways, so they're looking for acceleration. Quantity represented by the slope is magnitude of acceleration. We can't tell the direction of the acceleration because with speed we don't know anything about direction. Slope is magnitude of the acceleration. That is the answer, I guess, for 62. Calculate the distance the marble traveled in the first 3 seconds. All right. The easiest way to do this would be to Let's see, how fast is it going in 3 seconds? 4 meters per second. All right, the easiest way to do this is distance traveled equals average velocity times time. You get that from the reference table with the graph. All right, so we just need to know the average velocity. The average velocity isn't 3. That's the final velocity. The average velocity occurs halfway. This is linear. It starts at 0, ends at 4. The average velocity is smack dab in the middle, which is 2 meters per second, is the average speed. In this case, not average velocity, because we don't know the velocity, because we know nothing about direction. All right, so the distance traveled is 2 meters per second times 3 seconds is 6 meters. All right, so that is the answer to the distance traveled. Now you could have also found the area under the curve. Those of you fancy pants math people who like their calculus, that is the integral. It's the area under the curve is also. So D equals area under curve. And if you're in calculus, you know that that is the integral of v dt from 0 to 3 seconds, if you know your integrals. Anyways, the area under the curve is, we don't need calculus. We don't need to be able to do an integral, because we can calculate this area. It's 1/2 base, which is 3 seconds, times height, which is 4 meters per second. And we still end up with 6 meters, which is a good thing. One more question, and then we're done with the bees. The graph below represents the relationship between weight and mass for an object on the surface of planet X. Determine the acceleration due to gravity. All right, we have weight, Fg, and mass, m. What is the slope of that graph? Let's get a mathematical relationship between weight and mass. If you look, G equals Fg over m. If you look at that in your reference table, Fg equals G times m. Just rearranging that. All right, so there we go. There's our y variable, Fg. There's our x variable, m. This is linear, and this is the slope. Slope is G, the acceleration due to gravity on that planet. What is the acceleration due to gravity on this planet? I need to find the slope. Slope equals delta Fg over delta m. And let's see. I'll use when the mass is 0, the weight is 0, and what else do we have? When the weight is 18 newtons, the mass is 6 kilograms. That's looking like 3 newtons per kilogram. G is 3 newtons per kilogram. That's less than Earth. On Earth, it's almost 10. What a wimpy planet X. I would never want to go to X. What a terrible G that is. I would be able to jump way too high. When every time I get excited, I'd smash my head on the ceiling. That would be terrible. Man, I'm glad I'm not there. All right, I think that's the end of the bees. I don't know, I'm not going to make it to C. I'll do C later, but I'm not going to be able to make it to C before the 2017 exam, because I got to get this thing out. It's going to take forever to render. I have to edit, and then I got to upload it to YouTube. But good luck. Good luck, and I hope you're doing well. C, they should have... it's probably easier to follow. The key to C is make sure you write everything down, substitute the units, answers the units, draw everything correctly. Usually the C questions aren't too difficult. But anyways, here you go. Good luck.
History. Physics.